Yay!
Yay! Let's do a little example of a magnetic torque balancing the gravitational force on something that's allowed to swing on an axis. So what I mean is, suppose I got a magnetic field and it's pointed up. It's in the plus z direction. And I have a little loop of current. And the little loop of current is kind of constrained to swing on the y-axis. So that side A is going to be still, but it can swing up. So initially, it's just sort of in the down position. And the idea is I turn on this current, and then it swings up at some angle theta. So what I want to know is, for some angle, like maybe 30 degrees, let's say theta. Oh, I have it down here already. Suppose if theta is 30 degrees, if it swings up, here's sort of the side view. So if it swings up 30 degrees and B is pointed up, there's the mu, the magnetic moment of that loop. What magnetic field do I need to get it to swing up and stay at 30 degrees? So what's going to happen is that the magnetic torque on the loop that's trying to swing it up and around the y-axis is going to be balanced by the gravitational force, because this loop, weighs something. It's got some mass. So we're going to balance those two things and see what kind of magnetic field we need. Okay, so we want to balance torques, right? Because if we balance the torques, then it's going to stay in one place. So the torque due to the magnetic field, the torque due to the gravitational field is just going to act at the center of mass of the thing and point down, right? So that's just going to be mg. The torque is mg times the distance away from the axis. And that distance is just going to be b over 2 times sine of the angle between the gravitational force and the vector to where the center of the mass is. In other words, between the gravitational force and this vector, right? And that's just going to be 30 degrees. There we go. So that's the gravitational part. The magnetic part, what's the torque due to the magnetic field? Well, that's just going to be mu times b times sine of the angle between mu and b. Well, if this angle is 30, I probably didn't draw it very well, then this angle is 30, so this angle is 90 minus that. So it's going to be 60. So that's going to be sine of 60. And so now all we have to do is just equate those two things, and then we're all set. Okay, so this means that mg b over 2 sine 30 is IAB sine of 60. What am I solving for? I want to know what magnetic field is going to make this happen. So B, the magnetic field that makes this happen, is just going to be mg b sine 30 over I times A. Oh, that's fine. I times A times sine of 60. And just to put some numbers in, just to see what this how this turns out. What did I say? I said I was like 8.2. What else do I do? A is 6 centimeters. B is 8. So it's just a rectangular loop. And the mass of this thing is 4.2 grams, just a thin wire. And so when you plug these things in, what you get is that B was like 0.025 Tesla in the z direction. There we go. So if you applied this magnetic field, you can get this thing to swing up and just sort of stay there. So this is how you would balance magnetic torques and gravitational torques.